Hello and welcome to our discussion of Chapter 4. We're going to briefly start talking about molecules and compounds today. We'll dive into how do atoms that we so in-depth looked at in Chapter 2 and 3 with their electron clouds, how do those atoms now take those electrons and react them into different types of bonding? So how do molecules come about and how do compounds come about? The first thing that we kind of want to explain is how are elements different than molecules, and how are they different from what we see on the periodic table and what we've spent so much time discussing in previous chapters. When elements react and form a compound, they are completely new substances. I love this example with hydrogen, oxygen, and water. When we think about the reaction between hydrogen, which is a diatomic gas, oxygen, which is a diatomic gas, meaning diatomic, two atoms are always bound in nature together. And what they form is H2O. We'll take a minute and balance those. Now, what we see in this reaction is the idea that we have two elements that are going to be joined together to form this new molecule. And what's interesting is that the reactants, even though they are composed of the same thing for the products, they are completely different substances. Namely, hydrogen is an explosive gas. Oxygen is necessary for combustion reactions, so you can think of it as being reactive in explosion reactions. And then there's water, which is used to put out fires. They're, yes, composed of the same atoms. They might be balanced so that we are thinking about the same number of atoms are here, same number of electrons. But when two or more elements combine, they form an entirely new substance. We see this with sodium and chlorine as well. Sodium is an explosive metal. Chlorine is a poisonous gas, yet somehow when they come together to form sodium chloride, we eat it every day on our food. That's table salt. And so what we're gonna investigate today in this chapter is this idea that how did the elements we just studied come together to form new molecules or new compounds. And we'll be able to dive into those definitions a little bit more, see their reactivity in elements, and see what are new properties of the products that they form. I want to start here with the two main types of chemical bonds, ionic versus covalent. There's a couple of new things out there that talks about metallic bonds. We won't be talking about metallic bonds in this class. Very interesting new way of thinking about how metals bond with other metals, but we're going to fixate on the two main types that are prevalent in most general chemistry textbooks. Ionic bonds and covalent bonds. Now, an ionic bond is going to be between a metal and a nonmetal. A covalent bond will be between two nonmetals. So there's going to be this big difference between how elements react dependent on their physical properties, namely the periodic trends that we just looked at. We'll dive into that in just a second. Let's just answer this question. What is a chemical bond? Now, a chemical bond is going to be defined as a force that holds atoms together. We've been talking about Coulomb's law a lot so far, attraction between electrons and protons. Opposites attract. That is defining our idea that protons are attracted to electrons, and that's a good thing. We like that. That is usually when we see energy lowering, meaning it becomes stable, whether we're talking about an electron, whether we're talking about a molecule. If we have a lot of attractive forces, those attractive forces mean energy is being released. It's exothermic. We'll look at Coulomb's law again and be able to plug in some values here. But when we think conceptually about Coulomb's law, opposites attract because overall the energy is lowering for the system. The system is becoming more stable. Like charges repel. These are things like 2 protons or 2 electrons. This is a sad day for us. We don't like being repelled. It's energy raising. And this literally means unstable or reactive. So once we start thinking about the force that holds the atoms together, when 2 atoms come together, hopefully their attractive forces are going to outweigh their repulsive forces. And that's what we're going to start to look at. Chemical bonds form because overall, they lower the potential energy of the atoms. We want the attraction to be greater than the repulsion. This would be the idea of potential energy overall decreases when bonds are formed. So what we see in nature is that forming bonds releases energy. The reason why is because the attraction between those 2 atoms, specifically the protons of one and the electrons of the other, those attractive forces releases energy to the surroundings. Forming bonds releases energy, which means the opposite for breaking bonds. Breaking bonds requires energy. We can think about forming bonds as exothermic, breaking bonds is endothermic when we talked about energy way back in Unit 1. So understanding this, what does this mean for 2 atoms? Well, let's just say that I had atom A over here. Here's his nucleus. He's got some positively charged things, and he has an electron in an outer orbital. We'll call this atom 1. On the other side, we'll have atom 2 with some protons in its nucleus and an electron in its outer orbital. Now, when these 2 atoms want to bond, one thing they have to keep in mind is that opposites attract. There's some attraction between one atom's protons in the nucleus and the other atom's electrons, and the same over here, attraction. These are the good things. These are what actually holds the atoms together. Now, what we do have to remember, though, is that electrons repel and protons repel. So there has to be a balance. There's going to be a balance between all of our atoms when they start to bond. They are trying to overall have their attractions more favorable than their repulsions. If in nature we do not see these bonds form, it's because they're not attracted to each other enough. Those bonds aren't forming because they don't have anything to put them together. if we do see a bond in nature, like water, water bonds to two hydrogens. Here is a covalent bond. How I know it's covalent is because oxygen is a nonmetal and hydrogen is a nonmetal. Now we'll decide what covalent means in beyond just the identity of the two atoms bound together, but that bond forms because it is energy releasing. The attraction between the hydrogen and the oxygen is greater than the repulsion between those two atoms. So there's something favorable holding those two elements together. And that's what we're going to investigate. For a definition, an ionic bond, beyond what we said, a metal and a nonmetal, electrons are going to be transferred. Now, specifically from the metal to the nonmetal. Why? For reasons that we just talked about. Metals have very low ionization energies. Nonmetals have very high negative electron affinities. So when we look at an ionic bond, we will see ions are formed. Why ions are formed is because of this periodic trend. Metals have a very low Z effective, and so it's very easy to take a metal to a metal plus one cation. Nonmetals have a very high Z effective, so they want to gain more electrons. So the nonmetal can go to become an anion very easily. So there's this transfer of electrons from the metal to the nonmetal. Metals give them up, nonmetals take them in. And so it's really an electrostatic attraction. That holds our ions together. Why we call it an electrostatic attraction is because we have opposites. We have a cation plus an anion forming that bond. And those opposite charges are going to attract. That's Coulomb's law. Opposites will pull together and they will be composed in this solid state of opposite charges. I'm just using pluses and minuses to identify the cation and the anion. Notice that these are alternating. What happens here is this is what we call a lattice structure. Think about when you plant a vine, if any of you had ever seen a vine growing along a wall or growing in a backyard, when you have a lattice behind it. Lattice is usually a structure that allows things to build up or to grow alongside. This alternating plus and minus creates the attraction between the cations and the anions that allows it to build up into what we know as a sample of an ionic compound. So in a solid state, when we have something like sodium and chlorine coming together to be sodium chloride solid, we have some sodiums. Sodium is the metal, so we know it's going to be the cation. We have some chlorines. He's the nonmetal, so he's going to be the anion. So this alternating sodium plus one, Cl minus one, builds up all of our alternating charges so that we can truly see, yes, there's one sodium and chlorine ion here that is represented with NaCl. What we call that is a formula unit. A formula unit will be the smallest whole number ratio of ions. So when I think about a sodium +1 and a chlorine -1, yes, they make sodium chloride. There is my formula. It's going to be called a formula unit because in reality, it's not just one cation and one anion. It's a lattice of a huge amount of cations and anions, right? It's this buildup. And we'll talk about lattice energy in just a little bit. We'll focus our discussion first on ionic bonds, and then we'll move into covalence. But I just want to get a definition of covalent bond before we continue. For a covalent bond, we have a little bit different picture. A covalent bond is going to be a sharing of 2 electrons. Specifically, it could be 2 or more, but we'll stick with 2, occurring between, specifically, 2 nonmetals. And I'll say here 2 electrons or more, but at least 2 in order to get that bond to occur. Now, why is this different? Why are we sharing instead of transferring? With 2 nonmetals, we have a very high ionization energy and a very high negative electron affinity. So these 2 nonmetals don't want to give up their electrons entirely, but they will share them in order to reach a stability. Now, if we kind of look back at that formula unit right there with sodium +1 and chlorine -1, we can hint to why there's a stability. We saw that there was a stability in forming specific ions because of reaching noble gas configuration. We talked about that a lot. So now the only difference between an ionic compound and just the formation of the ion stability is just bringing them together in the lattice. For a covalent compound, we do not see ions. There's going to be a stability in sharing electrons. We will share electrons to reach the noble gas configuration. So, the sharing occurs between the 2 nuclei, and it will be a very structured look. So if we think about hydrogens and oxygens in water, oxygen has an electron configuration of helium 2s2, 2p4. We see that in its outermost shell, we need 2 more electrons. So oxygen tends to make 2 bonds. Now it can make more, it can make less, but in general, why we see in water, we needed 2 bonds to make that molecule is because oxygen needed 2 more electrons. Once it reaches H2O status, it gains 2 electrons to put in its 2p orbital. So it becomes a 2p6. Same thing with hydrogen. Hydrogen has a 1s1 configuration. We know it needs 1 more electron. So it makes 1 bond. Hydrogen is very special. It only makes one bond and one bond only. The reason for that is because the principal quantum number n equals 1 only has an s orbital, and therefore it only can hold 2 electrons total. So very important to note that once we get into the second row and the third row and beyond, we can start seeing these typical things and atypical things. But hydrogen is very predictable, and hydrogen won't make more than one bond. All right, for a covalent molecule like H2O, this is not called a formula unit. This is called a molecular formula. Why it's called something else is because it's an actual number of atoms in the molecule.